we have quite a lot of factual recall within this question. So writing the equation for the reaction of phosphorus with an excess of oxygen, you've obviously got to know what the final product is going to be and what the oxide of phosphorus looks like. And it's P4O10. Now, you can then have 4P plus 5O2 goes to P4O10, but you may remember from where we look at the trend in melting points across period 3 that phosphorus exists as P4. So either of those would actually be valid. So then we're looking at a test that we could use to distinguish between sodium oxide and the product of the reaction that we have here, phosphorus oxide. We're going to add water, and that's the first mark that we get. Now, after we've added the water, we're going to measure the pH. You could talk about having a pH probe, you could talk about a specific indicator, and then you'll need to remember the correct colours for the named indicator that you've given. I'm going to work through on the basis of using a pH probe. Now, what you would find is that the pH will be below 7 for sodium oxide and it will be above 7 for the phosphorus oxide. And again, this ties in with some of the periodic trends that you have to learn. Metal oxides are basic and non-metal oxides are acidic. And the way that I usually tell my students to remember this is to think about sulfur dioxide causing acid rain. Therefore, sulfur dioxide is acidic. It's a non-metal oxide, so non-metal oxides are acidic, so metal oxides are basic. It's just one way that you can remember that vital information. So then we go on to look at crystal structures, and we're starting to deal with bonding now. Silicon dioxide and sulfur trioxide. Well, silicon dioxide, hopefully you are remembering the structure of it and you're remembering its similarity to diamond. It does have that same tetrahedral makeup. So it is a giant covalent structure. Sulfur trioxide as SO3 is molecular covalent, often referred to as simple covalent as well. As a 4 marker, I really recommend you stop and consider the structure of the answer that you're about to put down. It can be really, really obvious when somebody has started writing in stream of consciousness and you have to drag yourself back to get the key information in. And you can often contradict yourself. So, there are covalent bonds in the SiO2, and it's the actual bonds that are broken in a giant covalent substance. But in an SO3 sample, when you are melting it, you're not breaking apart the SO3 molecule. You're overcoming the van der Waals forces that are holding those small molecules together. So 2 of the marks here are going to be related to recognizing the bonding type and recognizing what's overcome when you melt them. 3rd mark is then for actually recognizing that covalent bonds are stronger than van der Waals forces. And the 4th mark is actually then relating that to the amount of energy needed. If the covalent bonds are stronger, then more energy is needed to overcome them. So then we move on to 6.5, write an equation for the reaction of sulfur trioxide with potassium hydroxide. This is the point that absolutely everybody should get to because it's told you what the 2 things are. And we've got an acid and we've got a base. We've actually got an alkali, but it is a base. So if it's an acid and a base, I know I'm going to make a salt and I know I'm going to make water. So I can use that if I'm not sure what the answer is to try to reason this out. And I know that SO3 can move to SO4. We know that from other areas of chemistry. So I therefore know that if I have a base containing potassium and it's reacting with sulfuric acid, for example, I'm going to end up with potassium sulfate. And I also know that an acid and a base will react to make not just a salt, but they will make water as well. So what's left then is the balancing. There is an alternative here that is accepted, and you will be familiar with hydrogen sulfate salts, and they often come up when you're looking at the reducing ability of halides, where we react the halides with concentrated sulfuric acid. So this would be acceptable as an answer as well. Now, if we look at 6.6, an equation for the reaction of an excess of magnesium oxide with phosphoric acid. So you've got to know that magnesium oxide is MgO, that's going back to GCSE, magnesium is +2 ion, oxygen is a -2 ion. You have to remember that phosphoric acid is H3PO4. Well, we know it because it's a catalyst in the direct hydration of ethene with steam. We also hopefully know that phosphate ions are 3-, so I need 3 of the +1 H's to counterbalance it. Now, again, when I look at this, this is an acid and a base, so I'm going to make a salt and water. Now, my salt is going to be magnesium phosphate, because phosphoric acid makes phosphate ions, and the start of a salt name comes from the metal in either the base or the acid or the metal on its own when we do them. And we know that water is the secondary product. Now, getting the formula of Mg3PO42 does rely on you knowing that a phosphate ion has a charge of -3. And it's those tiny details that are going to be the sticking points if you haven't got that command of the information that's required. In terms of the final part of this, 6.7, draw the displayed formula of the undissociated acid form when sulfur dioxide reacts with water. Now, SO2 plus H2O makes H2SO3. You know the structure of H2SO4 because you've needed to learn it for when you're using it mechanistically. But we're not making H2SO4, we're making H2SO3. Now, I know that it's going to be diprotic, so I know there'll be 2 OHs. I know that the double bond O will be present there, but I know that the final O can't be there. So I end up with this structure. And as I say, H2SO4 looks identical to this, but with another double bond O coming off.